Morning, good evening, everyone. Thanks a lot for joining our session today. It's my great pleasure to introduce the first speaker, Lenka Zdeborová from EPFL. So Lenka is professor at EPFL, where she leads the statistical physics of computational lab. Today she will talk about insights on neural networks from statistical physics solvable models. So the floor is yours, Lenka.
Thank you very much, Carola. So I'll share the screen to show you my slides, and thank you for the invitation to the workshop. I was really hoping to be there with you guys, but yeah, that turned out still kind of tricky. So online like this, at least. So this is a very generic title that I often give when I'm asked the title very much ahead. But I will be the works that I will be covering today are in collaboration with this list of colleagues and students. And what the talk will actually be about is about this long-standing question of why doesn't backpropagation head for poor local minima? So this question that was posed, I purposefully here put a snapshot from this piece that Leo Breiman wrote, Reflections After Referring Papers from NeurIPS, 25 years ago. So that's a very long-standing question. And actually even, I would even make it a bit more precise. We don't even need to say local. Already, why doesn't backpropagation head for poor local minima? Because kind of from recent investigations of state-of-the-art deep neural nets, we actually, since they are so overparameterized as they are, we actually know empirically that, and also in some special cases theoretically, that there are global minima with bad generalization error. They do exist and they are reachable by stochastic gradient descent. Here I give a paper on the subject that I like very much. So we don't even need to think about local minima. So how comes that gradient descent algorithms manage to avoid those bad global minima with limited number of samples? So in the literature, this question is asked often, and you have works talking about implicit regularization of the algorithms, or things like learning simple functions first, and others. Here also you read about that there are no bad local minima. So this one I cross. I mean, to me at least, it's clear that there are bad, even global minima, and I think we all kind of agree that, or at least to me, the satisfactory answer to this question is not out there yet. So I will not be giving it today, but kind of showing you several works on our path to get there one day. So with that, to summarize, what the goal will be is to analyze the generalization properties of gradient-based algorithms in non-convex high-dimensional settings at low sample complexity. So the key points here really are non-convex, that's where it gets non-trivial. High-dimensional, that's the dimensions of what we are aiming to do today are high. And at low sample complexity, because in practice we do care about those constants, we do care about number of samples, whether it is 100 times what it actually should be. So I always try to aim at sample complexity as low as somehow information theoretically and tractably possible. So that's a ambitious goal, and answering it in general, as I said, is complicated. So most practitioners, when it comes to data, they have a fixed data set that they care about, and a lot of theory papers, or sometimes even applied papers, are actually evaluated on only a handful of data sets. You all know them. So that's a little limited scope of data sets that we often see in today's machine learning papers. On the other hand, in a lot of the mathematical theoretical literature, one tries to assume as little as possible about the data. that's a path that I do not like very much either, because in that setting, things get very easily computationally hard. So it's not clear whether that is actually relevant for the practical setting. So the strategy for today that we are trying to pursue is some kind of a middle ground that helps us to gain more insight, where we analyze generative toy models for data. And in those, of course, we want them to be non-trivial so that the question stays interesting and non-trivial mathematically. But we kind of put away a lot of the complications of the real data or of some more generic assumptions. So the generative process of real data that I will talk about today during the whole talk is what is known in signal processing as the phase retrieval. So phase retrieval is a signal reconstruction problem, but for the purpose of this talk, I will actually be looking at the very same problem, but more in the framework of neural networks, where I can actually think of what is the signal in phase retrieval, this W star. This will be weights of a teacher neural network. And then this, what is in signal processing, some kind of a measurement matrix X. In the framework of neural network, that will be the input data X, as we usually denote them. And then this teacher neural network multiplies the weights by the input samples as usual, and takes some function on the scalar product that in the case of phase retrieval is just absolute value. Here, all X and W and Y will be real valued numbers. So it's kind of a real valued phase retrieval. In optics, these are actually usually complex values. So this is the modulus of the complex number. But in this talk, everything will be real valued. And the teacher neural network then hands the pairs of labels Y and inputs X to us, the data scientists. And the problem that we will be looking at in this whole talk is the regression from the training data. So if I hand you this training data, and I don't even need to tell you how I generated them, you can deal with them as you would usually if you are doing machine learning and I tell you to regress. We will study the procedures that are common today to do such a regression. Several of them. But before coming to the neural networks and regressing with neural networks, I want to just set the stage for what is actually information theoretically possible in this problem. And for that, I just remind you how you get what I call the base optimal generalization error. So if you actually know how the data were generated, so in this slide, we assume that we know that, then you can write a probability distribution of what were the teacher weights given what you observe, that is the labels and the inputs. That's the posterior that is linked to the function the teacher was using. The P out is linked to that function. And if you know how to average over that posterior, which of course in general is complicated because here the W will be is d-dimensional and D will be large. But if you knew how to do it, then the base optimal prediction of a new label, you should take the output of same neural network as the teacher was using. I mean, the same architecture, and the weights of that neural network, you should average them over that posterior. This way you obtain a label, and if you want to minimize the mean square error from the true label that the teacher was generated, that's the procedure to pursue. So this is of course different from what we usually do, which is the empirical risk minimization. But this provably gets us the minimum error that actually can be obtained from that number of samples. Number of samples here will be n. And this is something that we actually know how to analyze in the limit, as I said, where the dimension goes to infinity and the number of samples as well, and the respective ratio that I will call alpha stays fixed. So alpha is something fixed, say 2. In the paper that I cite here, we actually compute a formula for this limit of the expectation of the normalization of the posterior, which is called the free energy in physics. And this is the formula. This formula depends on 2 scalar variables, m and m hat. And these special functions here are just some integrals over scalar variables. So we took this limit of high dimensional and transformed this free energy into evaluation of an expression that depends just on scalar variables. So we simplified considerably the kind of problem. That's why I say we analyzed it, we kind of analytically solved it. Now, what is this free energy good for? That's a generative function for pretty much everything we are interested in, including the optimal test error or generalization error that is obtained using the following formula here, where the m star that we plug here is simply the m at which the supremum here is achieved. So once we actually evaluate this function here, it's very easy to compute the optimal test error. And this is all irrespective of what is the algorithm that we are using. This is information theoretic, so there is an exponentially costly algorithm that can do that always. But in this particular case, we also actually have an efficient algorithm that in some region of parameters is able to reach this performance. And that's called the approximate message passing AMP algorithm. What's really nice about him is the state evolution that's due to the works that I'm citing here a decade ago, that states that the performance of the algorithm can be evaluated using the same functional that I showed you on the previous slide, the same function of two variables. It's that instead of taking its global maximum, this supremum was over all parameter m, to get the performance of the approximate message passing algorithm, we actually take a maximizer of this function that is the one that has the worst error. So that's what the state evolution theorem tells us. So of course, if this function has a unique maximizer, then the two approximate message passing algorithm and the minimum mean square error are the same. And if there are two maximizers here, then the algorithm can be suboptimal. So evaluating this all together into one picture for the phase retrieval problem that I defined 4 slides back, we get the following picture of what is actually possible at a small sample complexity. I remind here the alpha is number of samples over dimension. And here you see I am around 1 and a bit more than 1. And on the y-axis, I actually show the mean square error of estimating the W star, which in this problem monotonically translates into the test error. And if this mean square error is 0, then the test error is also 0. And on the picture, we kind of see 3 particular values of alpha where something is happening. So the first value is alpha half, where actually the mean square error gets from 1. It's normalized in a way that 1 means basically random guessing, no information available. And above 1, one can estimate better or get a test error better than random guessing. So that's called in the literature the weak recovery threshold, that's alpha half. That's not the one that we will be most concerned today. Today, I want to talk about the threshold where the test error actually gets to 0, which information theoretically, irrespective of efficiency of the algorithm to reach it, would happen at alpha 1. So we would just need few more samples than the dimension. But the approximate message passing algorithm needs around 13% more samples than the dimension to get 0 test error. And that algorithm is conjectured to be optimal among efficient ones, where of course among the class in which it is optimal, that's a big open question how to actually formalize it. But it's one algorithm that gives us this performance, and it's not easy to improve if we want it to be fast. So that was about the base optimal. Here, just one physics slide, that this hard phase where the algorithm actually does not reach 0 test error, while that is information theoretically possible. It's kind of physically related to what happens to a liquid when we supercool it below the freezing temperature. So water can stay water liquid even below 0 degrees Celsius at normal pressure. And the kind of reason why that physically can happen is the same reason why the algorithm gets stuck at higher error than actually it would ideally be able to get. But that's just a side remark. Now, kind of to go towards more what we are interested today in neural networks and deep learning, I talked here about Bayes optimal estimation, but that's not typically what we are doing in deep learning. In deep learning, we train by empirical risk minimization. So my first kind of vignette here is about how straightforward empirical risk minimization for that same problem compares to the Bayes optimal estimation. So let me set up the empirical risk minimization. For that, the first thing I need to do is to write the loss. So the data that are generated as before, the teacher uses Gaussian IID inputs X, Gaussian weighs W star, produces labels, hides the W star from the student, hands to the student labels and inputs, and then the student needs to learn, the neural network needs to learn weights W by minimizing, for instance, here I write a square loss, but the square loss is the differences here are between the squares. That's kind of natural for the phase retrieval problem, since we took the labels were absolute value of the scalar product. The squares take care of that. If you didn't put the squares here and minimize just the usual square loss, then actually with such a regression, we would not learn anything, even at high sample complexity for this problem. With the squares, we will see in a moment that we actually do. And the algorithm that we deploy for finding these W's is the usual gradient descent, or here like gradient flow. So what is known in literature about the performance of gradient descent or gradient flow for this very problem is summarized on this axis. So here I remind you what the alpha number of samples over dimension is for the information theoretic result and this approximate message passing. And in the theoretical CS literature, the known results for upper bounds for above where a gradient descent is shown to work actually involve some factors that are polylogarithmic with d times dimension, so much bigger than something like 1.13. And if we change the loss function slightly to make it slightly more convenient for gradient descent, this work actually, recent one actually showed that the sample complexity can be pushed to large constant times the dimension. But if we simply try numerically, where here these sizes are the dimensionality of the problem. So this should not be P, I called it G before. This is a slide from a different talk. So here what I show is the fraction of success, how many times the algorithm actually finds empirically the zero test error as a function of number of samples over dimension, this alpha that stays the same in the whole talk. And as the system size gets bigger, it seems that things are getting slightly harder. There is this shift, roughly logarithmic to the right. And this may continue as the size is going to infinity. Maybe it will stop at some point later. This we don't know, but definitely it doesn't stop before, say, alpha 6 or 7. That kind of we can empirically conclude from this picture. So if I put it back onto my axis, I see that there is a gap between what the approximate message passing is able to do and what I get from the gradient descent from the numerics. And moreover, the 7 is maybe shifting towards the right? So surely there is a gap. So how can we kind of think of closing that gap? That's not satisfactory if we have to use 7 times more samples than we would actually need. So that brings us to the second vignette, because so far I said, okay, I have a loss, I minimize a loss, but we also know that deep learning is overparameterized. So far, I didn't put any overparameterization here. So why? Well, because from the Bayesian perspective, I know that the teacher didn't have any hidden units. So why would I be putting hidden units into the student? That from the Bayesian point of view doesn't make sense to purposefully mismatch the model. Nevertheless, let's look how it behaves. So in theoretical machine learning these days, when we talk about overparameterized neural networks, we usually have in mind some variant of kernel regression, maybe random features, maybe neural tangent kernel, but some type of regression where the first layer is fixed and the second last layer is learned, because those are possible to analyze using various methods. So those type of methods in the phase retrieval would actually need number of samples that grows quadratically with the dimension. So much more than the even 7 times the dimension that we were not happy with in the previous slide of the gradient descent. So that's not the type of overparameterization that will help us here. In order to get something with good sample complexity, we actually need to analyze a neural network that learns features. So it's overparameterized and with feature learning, and we are aiming here at linear sample complexity in the dimension. So stated like that, that's kind of a rare beast in the literature on theoretical machine learning. But here we have a case where we managed to analyze something like that. So all we do is, again, gradient descent on a loss that this time is overparameterized. So all I do here is that I add number of hidden units, m of them, where m needs to be bigger than the dimension for the next result to actually hold. So it's overparameterized somehow mildly, not it doesn't have to be infinite or anything like that, just bigger than the dimension. And then in this paper with my former PhD student and Eric van den Eyden, what we managed to prove is the following theorem that is kind of geometric. This one doesn't so far touch on the gradient descent. It's just about the geometry of that particular loss function. And it tells us that if we express the loss function in terms of a quantity that here I call A, where A star would be the same, would be just the weights of the teacher times its transpose, this hidden number of hidden units, M star of the teacher in our case is 1, and that's also what the theorem is for. And we call A the weight, the matrix of weights of the student times its transpose. Then we can show that for alpha that is smaller than 2, in terms of the A, the loss has other minima than the teacher value A star. However, for alpha, so number of samples over dimension that is bigger than 2, the probability that the only minima that is left there is the one corresponding to the teacher is positive. That's what we managed to show. And in these, now this is true when the dimension goes to infinity. Now, when in high dimensional problems, things usually concentrate. So that's something that we didn't manage to show here, but we don't really expect this probability to be, say, 0.1. It's either 0 or 1. So if we manage to show that it is bigger than 0, it's very reasonable to expect that it actually is 1. So kind of going with that as an assumption, and putting it together with another theorem that is kind of more basic that we have about the gradient descent for this particular problem that actually just states that indeed gradient descent here goes to a minimizer. So if there is only one minimizer left, then it must go to that one. And also looking at the numerics that confirms what I'm saying. So I wanted to conclude that in this overparameterized neural network that we analyzed, we need fewer samples than the gradient descent that we saw previously empirically. We just need twice the dimension of samples to actually find 0 test error with that overparameterized neural network and simple gradient descent, which is still a bit more than the approximate message passing, but we are getting close. So that's one kind of positive result about how overparameterization linked with feature learning helps in this particular phase retrieval problem. And the last vignette of my talk is about, again, deep learning doesn't use really gradient descent, it uses stochastic gradient descent. So can we say something about the role of stochasticity in this toy model of phase retrieval on the data as I was generating them? So we would like, again, to get something that we can also analyze, and often analysis of algorithms, gradient-based ones, is easier in the flow limit when the learning rate goes to 0. The usual stochastic gradient descent in the flow limit just converges to the gradient descent. So there, in a sense, we are not gaining anything. So for that reason, we actually defined a variant on the stochastic gradient descent that we call the persistent gradient descent, that has a non-trivial flow limit different from the gradient descent. So that's kind of what we liked about it. And it kind of morally keeps the similar type of stochasticity in there. So what's being done in the persistent stochastic gradient descent, instead of at every time step generating your mini batch at random from the full sample size, we actually have this variable s of t that decides for sample mu whether it is or not in the sample size. And then for each sample, we have a Poisson process that is deciding with time tau whether the sample is getting out or getting back in the mini batch. So that's why persistent, the samples kind of stay in the mini batch for a while and then randomly get kicked out and then again randomly get back in. And that actually, in that case, we can take the flow limit of the algorithm. And that's something that we know how to analyze, this time using what we call dynamical mean field theory in statistical physics that has been used to study problems in structural glasses and spin glasses. Here is a paper that does basically what we need in the context of a related problem, but not exactly the same one. So what this dynamical mean field theory does for us is again takes the dynamics in the high dimensional problems, where again the dimension here will be going to infinity, and maps it into dynamics of a single particle in a one-dimensional problem, but for some cost of the dynamics becoming non-Markovian and having a memory. But and that mapping kind of gives us an insight about what's going on here. I just flash how that scalar effective stochastic process looks like. So it's a process on this variable h that has effective Gaussian noise that can come from a type of white noise if it was there in the gradient flow. But even if this temperature here is 0, there is an effective Gaussian noise with a kernel MC, and there is also a memory term given by these kernels. Then we can self-consistently estimate from the process itself. Here are just the equations for that, but the details of that are not important. What I want to show is that after we defined and came up with this persistent stochastic gradient descent, we also realized that it actually works much better than the gradient descent for the phase retrieval problem. So here I'm just comparing for a couple of different sizes the accuracy of the persistent stochastic gradient descent as a function of the running time compared to the one of the gradient descent. And you see that it's consistently better and continues being so as the size grows. And this is at alpha 2.5. So from this, we can conclude that even without actually having any overparametrization, any hidden units, already the stochasticity in the persistent stochastic gradient descent needs fewer samples than just the gradient descent does in the phase retrieval problem. So roughly, we can go down to something like 2.5. So with this, I want to conclude. So I hope that kind of intrigued you in this talk about the phase retrieval in high dimensions and with Gaussian input data and Gaussian teacher ways, that it's a neat model to study learning with neural networks, and a lot of these kind of mysterious phenomena from deep learning shows here as well. So in particular, that the sample complexity can be decreased by using either overparametrization or stochastic versions of gradient descent. I show you this solvable case of feature learning in high dimensional overparameterized setting. And I showed you this persistent gradient descent that has a nice flow limit and that is able to do better, is analyzable and able to do better in this phase retrieval than the gradient descent. And then the very last slide is still continuing kind of arguing for this very setting to be interesting, because there are still many open questions that we, even such a simple setting where we assume how the data were generated, we don't understand many things. For instance, what is actually the sample complexity of the gradient descent? I kind of went through it and showed you the numerics, but what actually it is, if you want to analyze it, that's something that that still is a mathematically definitely open question. And how does it depend on the loss function, on the learning rate? Or another question, I showed you one architecture of overparameterized neural network that was able to reach sample complexity 2, But can other architectures and maybe combining the over-parameterized architectures with stochastic gradient descent need even small? We don't know. And what is the sample complexity of the gradient descent when the number of hidden units actually is not bigger than the dimension, but smaller than the dimension? This we don't know either. And what is the sample complexity of the stochastic gradient descent for any of the over-parameterized settings? And can we analyze it? This we don't know either. So that all that kind of to say that at least in my point of view, before we understand these simple settings where we assume a lot of knowledge about the data, we will probably have hard time to understand these questions in general. And that's all for what I wanted to share with you.
Thanks a lot, Lenka, for a super interesting talk. I think we have time maybe for one quick question. Yeah, and I see actually someone in the physical audience who wants to ask a question.
I'm not sure whether you can hear me. Maybe.
I can.
Oh, yes. Perfect. So for the persistent gradient descent, when you apply it, I mean, you need to like kind of solve this ODE that you have there. So how do you do that in practice?
Oh no, I'm not solving the ODE to apply it. So the way I apply it is just like the stochastic gradient descent. It's just that I draw the samples, the mini batches differently. But otherwise, it's pretty much the same algorithm as the stochastic gradient descent. It's just that the way I draw each mini batch at every time step is different. I just keep the samples in the mini batch for a while, and then I put them out and put in new ones, rather than resampling at every given time step.
Okay, thank you very much.
Thank you so much, Lenka. Thank you so much.
Thank you all. Feel free to email me if you have more questions for which we didn't have time. Thanks.